So in this video, we're going to look specifically at bond energy. So we're looking at chemical energy, so the energy related to the bonds between atoms in a compound. Okay, so we're going to look at breaking and forming chemical bonds. Now these all have specific numbers that go with them. Stronger the bonds require more energy or release more energy. But quickly to refresh, so if we think back to our chemical energy, specifically bond energy, it requires energy to break bonds and it releases energy when we form bonds. So that's something we're going to need to keep in mind. So breaking bonds requires energy. That means you have to put energy into the bond in order to break it. When you form bonds, you release energy. So you're going to get energy out of that. When we look at an overall reaction, we're going to look at the reactants and we're going to look at the products. So our reactants, we're always breaking. So when we're talking about breaking bonds, we're looking at our reactants in a chemical reaction. When we're forming bonds, we're looking at our products. And that makes sense because when you go from reactants to products, you're breaking those bonds to then form the new compounds. You're going to form new bonds. So our reactants are always going to be breaking, our products are always going to be forming. So then when we look at the overall, if we're trying to decide how much energy overall in the reaction is involved, we're always going to do our breaking bonds minus are forming. So you're always going to do your reactants minus your products. You're going to add everything up, all the bonds that you break, and then you're going to subtract all of the bonds that you form. Now when you do that, you're going to get either a positive or a negative number. If it's overall a negative number, that means it's an exothermic reaction. Okay, so you're getting energy out. If it's an overall positive number, it means it's endothermic. So you're going to have to put energy in to make that happen. So when we look at the overall reaction, so when we do breaking minus forming, if it's negative, it's going to be exothermic. If it's positive, it's going to be endothermic. So these symbols are also going to come into play when we're talking about just separately whether these are breaking or forming, releasing or requiring energy. So when it all comes together, if it's overall negative, that means energy is coming out. If it's overall positive, that means energy is going in. Okay, so let's look at some examples. So we're going to go through two examples of just molecules, and we're going to look at how much energy is contained in the bonds of those molecules. Okay, so our first one is going to be H2O. Now, there are some molecules we're going to look at where, because we know about chemical bonding, we know how to draw Lewis structures. Water is a pretty easy one. I'm going to expect that you know how to draw the Lewis structure for water. Now, it's not required to be able to solve this problem, but it's a lot easier to visualize the bonds if you can draw out what the molecule looks like. So if we take water and we draw it out, it's got two hydrogens. Our oxygen is going to be in the middle. There's going to be a single bond connecting the oxygen to each hydrogen. If you want to draw the complete Lewis structure, it's also going to have two lone pairs of electrons. Now, your lone pairs of electrons aren't going to play a role in your bond energy because they're not participating in bonds. So if you leave them off, that's okay. If you put them in, that's great too. Okay, so we're looking at these two bonds. So if I look at this structure, I've got a bond between my oxygen and my left hydrogen, so that's one OH bond. And then I've got another between my oxygen and my right hydrogen. So that means overall I have two OH bonds. Now, an OH bond has a specific amount of energy contained in it. So in your student success sheets, there is a table that looks like this. We also have printed copies in the classroom. We do not expect you to have this memorized. This is something that you will always be given. And this tells you how much energy is contained in each of those bonds. Okay, so if I go and I look at my table and I find my OH bond, OH has 467, my units are kilojoules per mole. Okay, so if I've got two of those bonds, one bond is 467. If I multiply it by 2, because I've got 2 of them in this molecule, so now I'm going to take my calculator, 2 times 467 gets me 934. Again, my units are kilojoules per mole. Now, depending on what the question is asking, this on its own is a positive number because we're not looking at any sort of difference because there's no reaction here, it's just the molecule. If you are forming water, that means it's going to be exothermic. This amount of energy is going to come out when those bonds are formed. If you're breaking those bonds, this is the amount of energy that's going to have to go in. So it doesn't matter if it's coming out or coming in, it's the same number. It would just change whether it's going to be a positive or a negative value. Okay, so let's look at one that's a little bit more complicated. So propane, which has the formula C3H8. This is one I probably wouldn't expect you to know how to draw, so I'm going to draw it out for you. Propane has this structure. So it's 3 carbons in a row, each connected by single bonds. There's a hydrogen at each end, and then there's hydrogens around each of the carbons. So each carbon has 4 bonds. So I've got 2 different types of bonds going on in this structure. I've got my hydrogen carbon bonds, and I've got 1, 2, 3, 4, 5, 6, 7, 8. So I've got 8 carbon hydrogen bonds. And then I also have 2 carbon-carbon bonds. So if I'm looking at the energy for this total molecule, I'm going to add those up, okay? Because I've got 8 carbon-hydrogen bonds, I've got 2 carbon-carbon bonds. So now I'm going to go to my table and I'm going to look for each of those numbers. So if I look at my table, my carbon-hydrogen is 413. And I've got 2 carbon-carbon bonds. My carbon-carbon is 347. Okay, so then I'm going to grab my calculator. I'm going to do 8 times 413. And then I'm going to do 2 times 347. And then I'm going to add those together, which gets me 3,998. Again, my units are kilojoules per mole, because those are the units of these numbers from the table. So, same as with my water, if I'm breaking all these bonds in propane, it's going to require 3,998 kilojoules per mole. In order to do that, if I'm forming a molecule of propane, I'm going to get 3,998 kilojoules per mole of energy out. So that's how you do just the individual molecules. It's pretty straightforward. Let's look at a more complicated example, and let's look at a reaction. Okay, so the reaction that we're going to look at is the combustion of methane. So we're burning methane in oxygen. And so our reactants are a methane molecule, so CH4. CH4 is just a carbon with 4 hydrogens around it. Okay, my other reactant is an oxygen. So oxygen has a double bond, and then it has some lone pairs of electrons. Now, my reaction equation is balanced. I have 2 of them. So for the sake of visualizing what's going on, I'm going to go ahead and draw 2 of them. Okay, and then my products involve a carbon dioxide, so a CO2, oxygen, 2 oxygens with a carbon in the middle. We've got some lone pairs if we want to be thorough. And then our last product is water, H2O. So we've got 2 hydrogens with an oxygen in the middle. We've got a coefficient of 2, so it means we've got 2 of those guys in our products. So you should be able to figure out the structure for water. You should be able to figure out the structure for carbon dioxide. You should be able to figure out the structure for oxygen. Methane is pretty straightforward since it's just a carbon and 4 hydrogen, so that's not that complex. I'd probably still give you the structure for that anyway, since it's not one that we're typically familiar with, although you have seen it before. But otherwise, most of these I would expect you to be able to draw on your own. And again, a lot of this is just for visualization. I think it's easier to count all the different types of bonds if you have the Lewis structures drawn out. Okay, so if we think back to our comparison of our reactants and our products, we're always going to do broken minus formed. Okay, so we're going to break all of the bonds in our reactants and we're going to form all of the bonds in our products. Okay, so we're going to break 1, 2, 3, 4 carbon-hydrogen bonds. And we're going to break 2 O2 bonds. Okay, and then we're going to form 2 CO double bonds. And we're going to form 1, 2, 3, 4 oxygen hydrogen bonds. So we're going to add up everything from our reactants. We're going to add up everything from our products. And then we'll subtract them. Excuse me. Okay, so now I'm going to go to my table and I'm going to start plugging numbers in. So if I look at my table, my carbon hydrogen is 413. My OO double bond is 495. I've got 2 COs. My CO double bond is 799. And then I've got 4 OHs. My OH is 467. Okay, so I'm going to start calculating my numbers. You can type all of this into your calculator if you want, or you can do it step by step. I'm going to do it step by step just for our example. So 4 times 413 is 1652. 2 times 495 is 990. 2 times 799 is 1598. And 4 times 467 is 1868. Okay, 1652 plus 990 is 2642 minus my 1598 plus my 1868 is 3466. If I do 2642 minus 3466, that gives me negative 824 kilojoules per mole as my answer. So if I wanted to do some analysis on this answer, so the negative is important because the negative tells me this is exothermic. It's what we'd expect. We're burning methane. Typically, if we're burning things, it's exothermic because we get energy out. So our number supports that. For every 1 mole of methane we react, we get 824 kilojoules of energy.